Now, when people learn Cassandra data modeling, one of the things they learn to give up is a database that does joins for you. Now, that feels like a very powerful feature, and it often is for smaller data sets. It becomes an expensive thing on large data sets, and it's a typical step in relational optimization to give up joins that you had started with at a smaller scale. However, Spark lets us add this back in. We want to approach it with some caution because they can still be expensive operations, but they are incredibly useful. Now, fundamentally, what they do is they combine values from 2 or more pair RDDs based on the equality of their keys. In practice, we can use them for things like enforcing referential integrity and doing schema evolution and data migration and things like that. They're really handy. We're going to use them here to solve a couple of challenges. Those are going to be a schema evolution for the playlists by user table. We want to add some features to that table, and we have to evolve that schema and transform the data to make that happen. We're also going to validate some referential integrity constraints for that same table. That's another feature that Cassandra doesn't natively have. You can refer from one table to another. That's easy. Any database supports that. But it's not asserting the integrity of that reference. That's a thing that we can go back in with a Spark job and make those assertions in a batch process. Let's take a look at how we do this. The join transformation performs a standard inner join. If you know relational databases at all, and you probably do, this behaves exactly the way you'd expect. We call join on one RDD, passing in the RDD that we're joining, and it will look for keys that have the same value, and it will create a new RDD containing records of those keys and collections of the values it finds. Now, on this slide, we haven't drawn the lines for you, and I'd like you actually to stop the video and just trace out with your finger on the screen, follow this through as an exercise for yourself, and watch the joining happen here between these tables. You've got the source RDD on the left, the other RDD in the middle, and the output RDD on the right. Go ahead and pause it and see the join take place. Now, if you did that, you'll note that the output RDD has 2 rows for K1. Now, why is that? That's because there are 2 K1 rows in the left-hand RDD with values V1 and V3. And you see those V1 and V3 values show up in the output. There is a single K1 row in the other RDD in the middle there with value W1. And so there are, as a result, 2 rows in the output RDD where that value shows up. Likewise, there's a single K2 in the left-hand RDD. In the right-hand RDD, there are 2 K2s, and so we still get 2 K2 rows in that output. K3 and K4 are not common to the 2 RDDs, so they don't show up in the output, this being an inner join. The left-outer join transformation works just like a left-outer join in a relational database, where we're getting records in the output that have common keys between the left table and the right table, and records in the output that correspond to all of the keys in the left-hand table. So if a key shows up in the left-hand table, but not in the right-hand table, it's still in the output. If a key shows up in the right-hand table, but not the left-hand table, it's not in the output. And of course, if the key is in both, it is in the output. So again, you might benefit by pausing the video on this slide and just tracing with your finger which keys are common to the left and right tables and whether they show up in the output. Likewise, right-outer join, except now the direction is switched. So if a key only occurs in the left-hand RDD but not the right-hand RDD, it doesn't show up in the output. But if it is in the right-hand RDD and not the left-hand RDD, it will show up in the output. And of course, if it's common to both, it shows up in the output. And finally, there's fullOuterJoin that insists on creating as many records as possible. It'll join what it can, but if a key only shows up in the left or only shows up in the right, that's okay. It'll also be in the output. This is certainly the most expensive kind of join because it is, by definition, going to return the largest potential result set. Now, let's look at a schema evolution challenge. Now, this is a problem everywhere. It's not like this just crops up in a database like Cassandra. Schema evolution is always hard. It's just even harder when you've got that much more data in your schema. Fortunately, Spark makes this a pretty achievable problem. So we're going to add a couple of columns to our table definition. We'll run the alter table statements, which you see here, to change the metadata. We're altering playlist by user. We're going to add a column called genres, which is a set of strings, and a rating, which is a float. So genres and rating are things that are in our movie tables. We'd like to bring those into the playlist as well. And that denormalizing step is a very common sort of thing to do in Cassandra data modeling. If you're not familiar with Cassandra data modeling, this is not considered an anti-pattern. This is considered a very normal way to model data. Unfortunately, we didn't see that coming when we first made this table, and now we have to transform the schema late in the game when data is already in the system. And you can see also, if you look at those table diagrams on the slide, what the schema looked like on the left and what it will look like on the right when we've added those two new columns. So let's apply some of these joins we've been looking at to make the schema evolution happen. Let's walk through the code. First, we'll make an RDD for the playlists data. We're not being terribly picky. We're getting all of the playlists by user. That could be a very large RDD if this is a successful site. But we're selecting the user ID, the playlist name, the release year, the title, and the movie ID. And we are making that into a tuple that contains movie ID as the first entry, and then all of the other metadata as a tuple for the second entry. So kind of our own definition of the key value pair there. That's the playlists. We're going to do a very similar thing with movies, and note on that final line in the second block there, creating the movies RDD, we are doing the same mapping with as, making the movie ID, that UUID, as effectively the key of this pair RDD. The value there is going to be the genre and the ratings. So it looks like we're going to have everything we want here all lined up to go into this new table. Now, we step back just a moment. I want you to look at this slide and remind yourself of the schema. User ID, playlist name, release year, title, movie ID, genres, and rating. UPRTMGR. Let's take a look at that. Back to the code. If you look at that join at the bottom, we are joining movies to playlist, which Spark is going to do on the basis of movie ID for us. It'll give us a value in that pair RDD consisting of the value of playlists and the value of movies. That's that first tuple, that's U, P, Y, T. That second tuple, that's G and R. And we're effectively going to flatten those out into a single tuple whose values happen to map neatly to the columns in the migrated schema of the playlists by user table. That's going to allow us in the final line to save to Cassandra to the playlist by user table in a fairly trivial way. The mapping is going to happen for us from the tuple to the columns because we did our join in a smart way.